Welcome to a webinar on oil mist lubrication. My name is Heinz Bloch, and I'm doing this webinar in their Reliability Services group. I have been involved in oil mist lubrication for well over 40 years, many of these years with this particular company. My background is that for several decades to be exact, I was Exxon Chemical's principal machinery specialist for North America, and have had involvement in a large number of oil mist installations, all of which have been eminently successful. So what we would like to do today is first go over an agenda of things to be discussed, and then of course give you highlights of the success that industry has had with this kind of technology. We have four main agenda points today. First, we want to identify the root causes of rotating equipment failures, briefly talk about that. Then we outline the challenges that we have with traditional lubrication methods. Our third point would be to discuss the benefits of oil mist technology and discuss how it works. And finally, point 4, to review retrofit oil mist applications in existing plants, how complex or actually how easy these are. We want to be familiar with the current environment for refineries. There is, of course, an ongoing focus on increasing plant uptime and have as few unscheduled outages as is reasonable and possible. Maintenance cost reduction, cost avoidance is very critically important. Rotating equipment failures are the key reliability challenges. Sustainable solutions require getting to the root cause and not to have repeat failures. And finally, reliability focus calls for proactive versus reactive measures. So again, these 4 points, we want to reduce unplanned downtime. We want to improve the mean time between repairs or failures. You'll see later on that we call them either MTBF or MTBR. The third point was that we want to reduce maintenance costs. And finally, we want to increase the energy efficiency. There's room for improvement. I'd like to really point out to you here that the statistics available in 2016 are showing that ANSI pumps, which stands, of course, for the American National Standards Institute, pumps that have been standardized in accordance with that standard, typically have a life expectancy or repair frequency of once every 2.5 years. There are ANSI and ISO pumps, International Standards Organization, which on average in Scandinavian pulp and paper plants get far more life, 3.5 years. So on a percentage basis, that's 40% greater life. The API, which stands for American Petroleum Institute pumps, on average in the United States, they get perhaps 5.5 years as a mean time between failures. In Western Europe, slightly more, 6.1 years has been estimated. Then API pumps for a repair-focused refinery in a very, I don't want to say backward country, but certainly in a country where technology is just in the first stages of development, can be as low as 1.6 years. Then some data from the Caribbean region in Central America shows that 3.9 years is feasible in refineries. API pumps in the best of class company in the United States is reaching actually a life expectancy of 9.2. And then there's a petrochemical plant in Texas which reaches 10.1 years, mean time between failures of pumps. So all pumps in the major petrochemical plants in the US reach perhaps 7.5 years. And this is just now a gauge that allows you, the user, to attempt to find out where do I stand in terms of the reliability that I presently see in my facility. Why do pumps fail? Well, over 80% of pump failures are really attributed to bearing and seal failures. Combination of bearing failures and seal failures, as you can see on this graph, is perhaps 83%. And the remaining 17% are distributed over hydraulic issues or static joint issues, couplings, and so forth. In any event, we have to pay attention to bearing life. We have to pay attention to mechanical seal life. Particle contamination is really the leading cause of bearing failures. Particle contamination occurs in roughly 40% of the incidents that one has cataloged that relate to ultimately bearing failure. So we have to keep particles out, and we will see in a few minutes how oil mist can do that very effectively. There's also corrosion, overloading, misalignment of shafts. Incorrect disassembly is sometimes responsible for failures to appear on some of the components that we have taken apart. First, before we go into the generalized statements on what industry has achieved, I'd like to confine myself to a Petronor refinery, which is in the northeastern part of Spain. There are 183 machines that are equipped with oil mist, and an additional 610 machines are presently scheduled to be converted to oil mist. So there will be, in the very near future, a total of 793 total machines with oil mist. And the Petronor refinery has gone through very rigorous justifications, cost justifications, to identify what is really the payback, what is really the reason, how we can easily justify going with oil mist. The oil mist maintenance savings were cataloged as of 2012, and you can see how these savings progressed from 2012 until the beginning of the first quarter of 2016. The expectation is that there will be a continuing reduction in repair frequency and also a great reduction in maintenance costs. These are valid data that are amounting to many thousands of euros, as you can see on these bar graphs. There's a crude unit that has 55 machines that are operating on oil mist, and the mean time between failures in terms of days increased from roughly 400 in February of 2013 to February of the year 2016, where they reached 1,200 days. So that is a very substantial increase in terms of the life of the equipment. And if you project these numbers, you can certainly anticipate that 1,600 days between failures is achievable and has been achieved at other locations. Before we go much further, I'd like to just highlight what oil mist lubrication technology in general really relates to. We can see here a cabinet. It's on the right side. Inside this cabinet, and the door is open right now, we have an oil mist generator, and we have also a small container in which the bulk oil is contained. There are pipes that you see on top. We would normally call these pipes a header. And one of these headers is feeding the oil mist towards the machines that are being oil mist lubricated. You can see electric motors in the foreground. And usually these electric motors, of course, are driving pumps. But as you will see later on, other machines are connected to the oil mist system as well. But the second header is the return header. In other words, any oil mist that has gone through a particular bearing in a particular machine, that oil mist, after it has lubricated the machine, can be recollected. Instead of being sent off into the atmosphere, we can collect it. We can recondense it, and we can reuse it in many cases. Oil mist is a centralized lubrication system. You have just gotten an idea of what it looks like as a system. And it continuously and very efficiently atomizes oil into very small particles and then injects these small particles into carrier air. In other words, it's pure instrument air that carries these small particles or these small atomized globules of oil and delivers them to the bearings and to the metal surfaces that comprise, of course, the parts to be lubricated in a machine. The result is that you have improved lubrication, fewer failures, fewer repairs, lower life cycle cost, and extended machinery life. Again, we show a systems setup, and the oil mist generator, which you have seen on one of the previous slides, is shown in the foreground. The collection container is the vessel that is standing right next to this oil mist generator, and you can see that there are pipes that are illustrated in different colors. The one that comes from the oil mist generator is shown in red. That is the one that delivers the oil mist to the various points of lubrication. And The one that is shown in a mustard color or slight brown color, that is the one that is pulling off all of the remaining oil mist that has not actually condensed in the machine itself. A close-up view will show us a distribution header. This was the distribution header that we had seen earlier in the slide that preceded. From that header, we go to a mist manifold. A mist manifold is simply a convenient location where several tubes can be tied in. These tubes are then leading to the front bearing of a pump or of an electric motor and to the rear bearing. So the tubing, as we say here, routes the mist to locations behind each bearing. We will see that in another slide, just to make sure that we see the exact details. But also what is indicated here is a so-called reclassifier. The reclassifier goes into the mist manifold. So we have perhaps 4 reclassifiers that are threaded into the mist manifold. And out of each of these reclassifiers comes the tubing, which leads to a particular bearing location. In the lower left of this slide, you actually see an oil collection container. Now that is not to be confused with a very large container that we previously saw to the left of the oil mist generator. This is a collection container where any kind of liquid oil that has been liquefied in the process of going through the bearing can be collected. And it can either be drained into another container or it can be pumped back into the return manifold. Here is the slide which is of great importance because it shows the path that is taken by the oil mist through a bearing. You can see that on the extreme right we have a thrust bearing. These are 2 rows of bearings, and we let the oil mist enter into these 2 rows of bearings in a location that is between a seal on the extreme right on the shaft. You can see a small diameter seal. So the oil mist is introduced into the bearing between that seal and the bearing itself. And the oil mist now passes through, in this case, the 2 thrust bearings, and it goes into the center of the bearing housing. The same thing is happening with the so-called radial bearing on the extreme left. The radial bearing is to the right of another one of these oil seals. And the oil mist is introduced between the oil seal and the radial bearing. After the oil mist goes through the bearing, it is going to commingle with the oil mist that is already now existing or simply has formed as a result of introducing mist from the right side bearing. So all of these leftover oil mist elements, they combine and they are now in the middle of the bearing housing. And as you can see at the bottom of the bearing housing, we have a threaded connection that can be connected to a collecting tank. Safety of an oil mist system is fairly easily explained. Oil mist is non-combustible. It's an air-oil mixture, and typically it is a volumetric ratio of 200,000 volumes of instrument air with 1 volume of oil. And the oil is, of course, atomized, as we mentioned earlier in this webinar, and it is so lean that it cannot in any way sustain combustion. It is not an explosive mixture. It is substantially below the sustainable burning point. And experiments have shown that the concentration of oil mist in the header ranges from 0.005 to as little as 0.001 1/1000th of the concentration that is generally considered flammable. Stray mist. As you have of course seen, if somebody leaves off the bearing protector seals, the seals that we showed at the extremities of the shaft, well then any mist that has gone into the bearing housing may migrate out to the open atmosphere. We don't normally want to do that, but it is also a fact that in the United States we do not expel more mist, even if we leave off these bearing protector seals, we do not expel more mist than what is presently allowed by the so-called OSHA requirements in the United States. The preferred way is, of course, that we don't even get ourselves into the question of how much mist is expelled into the atmosphere. We would much rather actually use the present state-of-the-art oil mist systems that are completely recycle stray mist preventive. And so the recycled stray mist is kept in a closed loop. Again, oil mist systems that completely recycle the mist are available, and they are referred to as closed loop systems. We had mentioned at the beginning of the webinar that while it's true that for the great majority of plants, it is centrifugal pumps and it is electric motors that are lubricated with oil mist, it is also possible to use oil mist for small steam turbines or for gearbox bearings. The requirement generally is that we have to be dealing with rolling element bearings, all types of rolling element bearings, whether they are ball bearings or perhaps tapered roller bearings or perhaps cylindrical bearings, makes no difference. As long as it's a rolling element bearing, it is a candidate for the application of oil mist. And thousands of these, and you will get the numbers later, have been in use and have been in service in my own personal experience for well over 40 years. It is indeed for over 40 years that I have been working with companies such as primarily Colfax to install, to understand, especially to cost justify these systems for refineries. Before we discuss the benefits of oil mist, we want to outline the role of lubricants. Lubrication serves primarily to separate metallic parts that are moving relative to one another, and we can greatly reduce the wear of these moving parts by having a lubricant between them. A second reason for having a lubricant is to provide cooling. We want to remove heat from the area in which relative motion occurs. A very important side benefit of proper lubrication is that we can have a cleaning effect. We can remove the particles that in some cases form in areas that move relative to each other. We can sweep them off. We can flow them off. We can eject them from metal to metal contact. And finally, of course, the lubricant, if it's properly selected, is protecting the parts against corrosion. In an atmosphere that's loaded with contaminants, for instance, steam or particles, dust, dirt, the lubricant protects the internal parts against the corrosive action of any of these contaminants. We want to see the difference, the primary difference between what we might call conventional lubrication, which involves an oil sump, liquid oil, and compare that to what happens with oil mist. And so getting back to these four principal reasons why lubrication is used in the first place, well, in an oil sump, the amount of lubricants to different parts really depends on how this lubricant is applied. Sometimes it's a so-called ring oiler. In other cases, we actually allow the lubricant to go to the center of the lowermost rolling element or bearing rolling element. In contrast with oil mist, lubrication takes place in a highly dependable manner because oil mist allows the lubricating of the total surface in contact, not just the surfaces that are in contact with the lubricant level at the bottom of a bearing. We look at particulate removal. Well, if you have an oil sump with liquid oil, then any kind of contaminants will actually drop to the bottom of that sump, but they're not being removed from that sump. And in some cases, they may even, in an agitated sump, if there is turbulent flow of lube oil, they may remain in suspension. And these particulates that have contaminated the oil will actually get into the bearing and cause early distress. Again, in contrast, oil mist has a very high rate of particulate removal because there is ongoing cleaning that is progressing. Oil mist is going through the bearing. If there should be any kind of debris for any reason being generated in that bearing due to bearing wear, well, then there is a high probability that we are cleaning that particulate matter and that we are flushing it off. The cooling is our third point. With an oil sump, cooling is generally rather poor. It consumes energy, it raises the operating temperature, and we will see in a few minutes on another slide how much the operating temperature can actually be reduced by using oil mist. In fact, in the right column under oil mist and under cooling, we use the word strong. There's a strong cooling action because we remove liquid friction, and liquid friction that is being removed or reduced is going to reduce our pump operating temperature or bearing housing operating temperature generally by as much as 10 degrees centigrade. Finally, we spoke about corrosion protection. An oil sump has an issue with corrosion protection, especially when a piece of machinery is not operating, it's standing still. So the oil, the liquid oil, is really only at the bottom of that bearing housing. The rest of the bearing housing is filled with ambient air. The ambient air frequently has dust in it. The ambient air very frequently has water vapor in it. And as we now have a piece of machinery not even operating, in the daylight or in the sunlight, I might say, we have a bearing housing that warms up. And as a result, the air inside that bearing housing expands and it gets expelled. And then at night, even with the equipment not running, you have a cooling effect because the ambient air is cooler. And as a result, the air that's in the bearing housing is now going to contract, and the pressure goes down a tiny bit compared to atmospheric, and the atmospheric air pressure is overpowering the seal area, and we are pushing moisture from that outside atmosphere into the bearing housing. Then, of course, in comparison, oil mist provides 100% protection because the oil mist is applied under a slight pressure. Usually the pressure is the equivalent of approximately 1.5 inches or something in the vicinity of 40 millimeters of water pressure in excess of the pressure that you have in the atmosphere. So again, corrosion protection is our last point. It's defective, especially on standby pumps. It only protects parts that contact liquid. The rest of that bearing housing has ambient air in it, and as this ambient air is going to be slightly pressurized due to sun exposure or the bearing housing warming up, we are pushing the air out, and at nighttime when the temperature goes down, we're pulling the air back in. In contrast, you have 100% protection with oil mist because it exists at a pressure of approximately 40 millimeters of water column in excess of the pressure of the surrounding atmosphere. I'd like to now talk about some case studies. The first case study you have heard about, it's with the Petronor refinery. Very compelling information, very up-to-date information. Older information that we have here in the United States. In a Western state refinery, oil mist was applied in a crude unit, in a fluid cat cracker, and also in the steam boiler area. And the effect was, in case study number 1, that we had reduced pump maintenance costs, eliminated lost production incidents, the discounted cash flow returns exceeded 200%. And finally, the payback in case study number 1, the payback was less than 1 year. Then we look at an overseas refinery, that's our case study number 2. The oil mist was used in the entire plant, and this overseas refinery was able to compare the results on the oil mist equipped plant with the results of a sister plant, which was identical, but didn't have oil mist. And the results showed that the MTBR, mean time between repair, similar to mean time between failure, really doubled for pumps and seals. And operating manpower was cut in half by reducing the lubrication cost in terms of labor and especially in terms of oil consumption. The payback in that particular instance was somewhat less than 1.9 years, 1.7 years perhaps. And that allows us now to go to the case study number 3. We're dealing with a mid-coast refinery. We're talking here about the US Gulf Coast, and 2 systems were installed on crude units. The pump bearing repair costs dropped by 88%. The discounted cash flow returns were in excess of 70% because the repair costs were fewer and because the repair expenditures, the manpower expenditures, were also lower. And there the payback achieved was approximately 1.5 years. Finally, there's a specialty polymer unit which had accurate data, and the failure rate dropped by 98% after oil mist was being applied. And the availability to actually manufacture and produce and sell polymer increased from year to year somewhere between 5 and 7%. That is a very, very sizable amount of increased production, which is directly applied to the bottom line as profits. The 4th point on the case history number 4 is that the discounted cash flow returns without including increased production exceeded 400%, and the payout was less than 6 months. We can summarize to some extent by speaking about the value of oil mist. We have alluded to reduced repair costs. Repair frequencies have been reduced. The efficiency of manpower is greatly increased. The manpower that we save by not doing conventional lubrication, that is manpower that we can apply elsewhere in our plant to do some important work. We certainly have reduced oil consumption, and oil consumption rates, generally speaking, are 60% less with oil mist than they are with conventional lubrication. We will have a slide in a minute that explains why. And also we have increased fire safety because the oil mist is of course non-explosive and does not sustain a flame. So speaking of reduced repairs and failures, there are 2 similar olefins plants with 200 pumps each in the Gulf State region, in Texas to be exact, and one of them without oil mist had a number of pump repairs that is plotted on the upper graph. And in one particular year, it reached something in the vicinity of 50 pump repairs in that year. But with pure oil mist, the sister plant reduced its failure rate by a full 90%. And you can see that on the lower graph, where on average we had perhaps only 6 or 7 pump repairs on a per year basis. We now look at a slide that originated with 2 Shell refineries in the Houston area. The 2 refineries wrote a paper on their experience, and on the left you can see that the number of failures with oil mist were as low as 10 in a 3.5 year time period. On the right, you can see that they had 75 failures in the same 3.5 year time period. So without oil mist, frequent failures of electric motors, with oil mist, very infrequent failures. And they truly were able to compare 2 identical refinery locations, even in the same geographic area of Texas. On another slide, we can have a comparison of 2 refineries that had 600 pumps each. And the upper graph shows that with oil mist, the mean time between repairs, close to mean time between failures, was on average reaching as high as 9.5 years. And on the bottom, without oil mist, the failure rates, or the MTBR of these mechanical seals, was in the vicinity of maybe 3.5 years. And on the lowermost scale, the x-axis, you can see that this is data that relates to a year, and we have the graph separating the different months from September through November to January of the next year, and going back to September of the following year. And the result was, of course, drastic. But the question now is, why were mechanical seals affected here by oil mist? After all, the mechanical seal is not exposed to oil mist. That statement is, of course, correct. But going back to this slide, I'd like to remind you, as you listen in on this webinar, that it is very frequently the bearing that brings down, that causes a consequential damage of the mechanical seal. So by looking at mechanical seal failures, we are actually in many cases looking at bearing failures that have preceded it. But mechanical seals are usually of great importance to us because they cause serious emissions. And so this particular plant, or the two plants in question here, they were more interested in mechanical seals, but they did realize that with oil mist, seal failures are being reduced because the bearings live longer. On this slide here, we're dealing with the reduced repairs and failures that happen when we decrease the contamination with water in turbine bearings. Water gets into turbine bearings, as we will see from another slide in just 2 minutes. Water gets into these bearings because there is steam leakage. So this Italian refinery was extremely interested in finding out to what extent can they reduce water intrusion into small steam turbines. And the answer is the water intrusion that they had in the year 2010 typically was in the vicinity of 1,800, 1,900 parts per million. And after a brief time period on oil mist, filling the bearing housing with oil mist, the amount of water contamination went down to in the vicinity of 50 parts per million only. And that's what you see plotted on the extreme right of this graph, where in the time period from the 25th of August 2010 to the 29th of November 2010, consistently every month they monitored the water contamination. It clearly went down to 50, where previously it had been 1,900. So we want to recap here, how does oil mist reduce seal failures? Well, remember that the bearing is mounted on the same shaft as the mechanical seal. And fewer pump failures means that you have reduced risks of exposure to chemical agents. And the root cause of pump failures is very often misdiagnosed. It's a chain of events that very often begins with inadequate lubrication, and finally it culminates in rapid seal failure. So it is a fair statement, a correct statement, to attribute fewer mechanical seal failures to better lubrication of the bearings. We look at an API standard. It's an API standard that covers mechanical seals, and it's especially relevant and important to have good mechanical seals in such units as the hydrofluoric acid alkylation unit. We call it an alky unit very frequently. There's a paragraph in that standard, it's paragraph 3.3.3, which says provision should be made for monitoring large pumps and drivers so that vibration is not excessive and so that bearing housing temperatures are not excessive, because we want to have zero failures that could result in emissions of this very dangerous fluid. And so the API standard specifically says that alternative lubrication systems, alternative to the traditional systems, the alternative system being an oil mist system, may be beneficial in reducing bearing failures that could cause seal failures. So here we have again an independent corroboration of the fact that with good lubrication of the bearings, we have increased life expectancy of mechanical seals. The reduction in lubrication-related labor hours we had mentioned very early in the webinar. The yearly savings here in two refineries with 600 pumps each were again compared to each other. And the one that had oil mist was reducing its labor expenditure by $115,000 in a time period of approximately 3.5 years. And so that's what you see on this slide. Then we have a reduction in oil consumption. I mentioned earlier in the webinar that it is typically 60%, but here in these two refineries it was 71%. And so why do we have a reduction in oil consumption? Well, obviously, we are no longer in need of replacing the liquid oil. We are sending only atomized globules of oil in mist form through these bearings. And as a result, we really are using fresh, clean oil throughout. And that in itself is allowing us to keep the oil, even if we collect it later on, keep the oil in service for a much, much longer time, typically approximately 4 times as long. And we have a slide that explains that as well. For now, remember that we are again dealing with 2 refineries, and that these 2 identical refineries were able to closely observe the lube oil consumption in one unit as opposed to another unit. And because of the oil mist using nothing but highly filtered oil and not recycling debris, they were able to really have a 71% reduction in oil consumption. They no longer had to drain the conventionally lubricated bearing housings because they no longer had conventionally lubricated bearing housings. A bearing temperature decline of somewhere between 10 to 20 degrees Fahrenheit with pure oil mist, and every 10-degree drop typically is associated with an 11% increase of bearing life. Please pay attention to where it says oil bath lubrication. That would be the conventional lubrication. Well, if we have conventional lubrication, we have to change the oil after a time that we have labeled on the horizontal scale as T sub 1, because we have now an increased concentration of debris, the oil has gotten hot, and as a result, as a precaution, preventive maintenance with that kind of lubrication, the traditional lubrication, one changes the oil at time T1. Whenever you have a contamination level which reaches a certain ISO number, in this case, you can see next to the horizontal black line, the ISO number is 22/19/16. That is when the bearing manufacturer insists on changing the oil. So you change the oil with conventional lubrication 3 times as often, at least 4 times as often in many cases. You change it at time T1, T2, T3. If you have oil mist lubrication, well then if you reach with oil mist lubrication an oil cleanliness level that is shown next to the red line on the vertical scale, a cleanliness level of 18/15/12, well then you have oil that is as clean as the sump oil was to begin with. But the good thing is that if you look at the green line, the lube oil in an oil mist system has such great filtration, and that can be explained to you again by the Colfax company. It has such great filtration that you normally reach 16/13/10. And as a result, we will see on the next slide, the life expectancy of the bearings is greatly increased. On this slide now, we are describing oil savings. We are looking at the impact of superior filtration, which we get with oil mist. And so on this table, it says near the top, estimated life extension table. And also right below it, it says the targeted cleanliness level according to the ISO code. You can go into the column that is on the extreme left, which is labeled 20/17. You can go towards the right, which means much cleaner oil, and it culminates in oil that is labeled as 10/7. But these are the various columns. In these columns, oil that's not too clean on the left, oil that is very clean on the right. And if now we have an actual or existing machine oil cleanliness level that is on the vertical scale, the Y scale, let us use an example. And the example that we're using is that if you presently have an oil that has a ISO code cleanliness of 22/19, that would be on the vertical scale, 22/19, and you have a targeted and actually achieved cleanliness level of 17/14, well then where these rows and columns are intersecting, that is where our example points to. And for rolling elements, having gone from a previous 22/19 to now a new achieved 17/14, you can see for rolling element bearings the number 2.5. And that means that the bearing life has increased by a factor of 2.5 by simply using cleaner oil. If you want to stay in the same row, and the row, remember, is 22/19, and let's say you started with that cleanliness level, and you go all the way to the right, where you have achieved a new cleanliness level of 10/7, well, in that case, the bearing life would be extended by a factor of 10. So this is how you use these filtration impact and life extension numbers. Life extension, not so much of the oil, but certainly life extension ultimately of the bearing. We will talk briefly about oil mist applications in existing refineries, retrofit applications of oil mist technology. First of all, oil mist works equally well in new greenfield plants and also as a retrofit solution for existing refineries or process plants. On the second point here, it says for retrofit applications, the fastest returns are seen on pumps and motors, where presently you have failures more often than every 48 months. In other words, if you fail motors every 36 months or every 28 months, then that would be a candidate where without any difficulty, you will see cost-justified modifications in oil mist. You will certainly be able to increase the life expectancy of these motors, the mean time between failures, from previously 36 or even 48 months to something well in excess. And the same is true for steam turbines in units that work with hot products. A good example would be the FCCU, the fluid cat cracker unit, or the coker unit, and that's where you have hot products. If you convert pumps and electric motors to oil mist lubrication, you will very rapidly see an increase in life expectancy and a decrease in cost of lubrication. Your third point here, third bullet point, says when both motor and pump are using oil mist, the payback of 2 years is quite normal. And finally, oil mist, it's a big number here, is 99.99962% reliable because there are no moving parts. So you may ask now, well, if oil mist is 99.99962% reliable, what happens in terms of its unreliability? The answer to that question is that the unreliability is usually something that has been caused by human beings. If you allow the oil mist generator to run without having any oil supply, without having refilled the refill vessel for that oil mist generator, well then of course there is no longer any mist being generated. But the very fortunate thing is, if you go back to the very first slide or the very first slides, you will see that there is supervisory instrumentation and the supervisory instrumentation is going to warn the operator of a malfunction. And then, generally speaking, the operator can really almost immediately refill, for instance, the oil reservoir, and there will be no failures of the pump, because the pump or electric motor, in the 8 hours that it has run without that external oil supply, it will still have a sufficient amount of oil that is clinging to the rolling elements of the bearings, and as a result is adequately separating the rolling parts of the bearing from the non-rolling parts. So it is highly, highly reliable, and in the few cases where the operator makes a mistake, even in those cases, the operator goes out and is able to save his unit. Here then we see a retrofit application, very straightforward. One removes the constant level lubricator. Sometimes we use a brand name for these lubricators. Trico is one, very good lubricator generally speaking, but by removing it and converting to oil mist, you no longer have any concern as to, is my workforce diligent and are they doing the proper setting of these oilers? Are they doing the proper installation of the entire shaft system? Because I would like you to look at the larger part of this slide, and you can see that to the right and to the left of this Trico lubricator, there are so-called oil lift rings or slinger rings, and these slinger rings will work properly only if that entire shaft system is absolutely horizontal. If that shaft system isn't absolutely horizontal, these rings will touch the inside of a bearing housing, and they will actually either slow down or they will have abrasion and contaminate the lubricant, which in turn causes the bearing to fail prematurely. The next thing to do is you ask yourself, how do I retrofit oil mist to electric motors? Well, what you do is you don't even have to shut down. The modification process means that you open up the grease plug at the bottom of the bearing housing, you use an air gun at the grease inlet, and you don't use excessive amounts of air, but with the air gun, you're pushing out the grease that is normally accumulated in the bearing area. And after pushing the excess grease out, you are inserting an oil mist fitting near the top, and you connect the oil mist fitting, and even with the motor running, one has had extreme success by making these modifications. One of the earlier slides had highlighted the benefit of oil mist on small steam turbines. And the image here on the slide clearly shows that we have steam leakage, and the leakage from the steam turbine itself is, of course, entering into the bearing housing. The bearing housing that we see here is probably a sleeve bearing. And so the oil mist is called wet sump, which means we purposely continue to use the liquid oil in that bearing housing. But the space in which we normally have air, that space is displaced and filled with oil mist at a pressure that is roughly 40 millimeters of water column in excess of the surrounding leaking steam. And as a result, we now keep out this steam vapor from the bearing housing, and we keep the oil clean. So this requires very little or even no modification for retrofitting. It clearly decreases water contamination if we insert or attach an oil mist tube to the top of the bearing housing, and the oil mist is keeping that bearing housing cool. And it means that where normally we would perhaps have grease in some of these bearings, the baking of that grease, the overheating of that grease is eliminated. The oil mist flows through the bearing top, and it goes perhaps out to the side. Liquid oil or grease is kept in a bearing of this type, and the oil mist routing is described in some of the literature that you can get from Colfax Reliability Services. They have very clear-cut instructions that allow you to follow point by point and to do this kind of work even as the machine is running. Then we will summarize here in the remaining 2 slides what is really the oil mist technology advantage. Well, oil mist has been lubricating rotating equipment since at least 1967, in my own experience, certainly since 1967. And as of today, the year 2016, more than 3,000 oil mist systems are serving a total of 150,000 or more pumps, and perhaps in some cases small steam turbines, and at least 25,000 electric motors. If you are experiencing a mean time between failures of lower than 6 years in any plant unit, then an oil mist retrofit is without question the best solution to increase your overall reliability and also the profitability of a plant. Finally, we want to say again that oil mist installations do not interfere with the normal operation of a unit. And you position your plant or yourselves as plant operators for sustainable maintenance cost avoidance if you go with oil mist lubrication. Look at the statistics that are available and which clearly demonstrate that.